All right, we might as well get started today. Welcome back to the stream on Twitch. Welcome back to the video series on YouTube. If you like what we're doing, definitely please like and subscribe. Hit that bell icon to be notified when we upload new videos on YouTube. We really appreciate it. This series has been a lot of fun so far. The Breadboard to Marketplace series. So, as we left off in the last video, we were writing our test plan. We got to the stepper motor driver, stepper driver chip, and kind of wrote the test plan for that. So we have that part. Let me get this open so we can get the test log back open. I almost forgot about that. Test plan log. All right. So we've got all this stuff. So I should have dragged this down, but that's fine. It'll just pre-fill a couple things out. That's fine. Get rid of this stuff out of there. Perfect. So, subsystem test. So we want to pick up where we left off. We want to do the subsystem test for the fan. For one thing, to make sure that the connector is soldered right and it's got no problems. We've got everything wired up. And we can read the tach and the PWM. So one thing to keep in mind is, so the tach in these fans is, let me find the bomb. That's right, I moved everything around, so it's not going to be happy about me. I just want to bring this up, this data sheet, to make sure everything. Controller, outputs, the bomb, LibreOffice Calc. Okay. Yeah, you know what? We can probably, while we're in here, let's go ahead and get rid of all this stupid calling. Let's turn it all back to default. We don't need it anymore. No fill. All right, save that. We don't need that anymore. So let's get the fan. Data sheet on it. Just so everybody's tracking along. The diagram, the data sheet should explain the, yeah. All right. So I'll drag this over real quick. So basically, the sensor for the fan, it's essentially a Hall effect sensor. Basically a transistor. Basically an NPN transistor. Let's just look at it that way. So Hall effect NPN transistor. So you have you're pulled up to your 3.3 volts, and then your sensor output, which we've got right here. So the fan tach pulled up to 3.3 volts, and what happens is, so when the fan's not rotating, it's a high. So you're going to pick up 3.3 volts. So you're basically looking for your falling edge, because every time it triggers this, the Hall effect system triggers this transistor. It's basically going to pulse that low. So it's going to keep pulsing that output low. So you're looking for, you're basically looking for the falling edge of a pulse. And like I said, I've got firmware already written, header and source file for PWM fan that we're just going to go and pull into this. It does everything we need. We can customize it, but I don't think we'll have to, because we're just going to be doing tach reads just to verify. We're going to be actually setting PWM values in it. So this is just because, to give you an idea what we're looking for. So we're just looking for falling edges in the pulse, because it's the way it's designed. So the tach and then the PWM input it's basically just a PWM output off the ESP32, just to control speed. And I've got, like I said, code that actually works. I should have left the data sheet open, but the fan has kind of like a minimum duty cycle before it even kicks in. So up until we hit that point, it won't even rotate, and then up to maximum speed. So we'll take all that into account through testing and stuff. But we are going to rate that as a test. Subsystem test 14. Okay. And stop. Disabled. Connect. So what we're going to need to do is I'm going to need to get into Odo, because since we've created a part number for this guy, inventory, products. So I'll just drag this over here, make it easier. So here we have this guy. We actually have kind of an internal part number. So we're just going to copy and paste that. Connect a fan assembly to, make sure I get the right connector, CN6, and apply. At this point, the I notice there's no firmware loaded, and that's fine. Actually, you know what? We're gonna do this. We're gonna go ahead and rewrite this. We're gonna kind of like this. Disable. So we're gonna put this as a second step. Output. All right. So what we're going to do, that's going to be a second step to something we're going to do here. Yeah. Flash the fan test to the ESP32, then disable the benchtop power supply at fan to CN6, and then re-enable the power output of the supply. So at this point, the fan should not be operating. So basically, the default settings for the firmware will to not be driving the fan. Make sure I can spell right. I kind of like the fact that I threw that spell check add-on extension into VS Code to help me catch my own mistakes. So the fan should not be operating at this point when you re-enable the power supply. Now, there's a chance that during the initial bootstrapping of the ESP32, the fan will kind of kick, and that's fine. Sometimes there's just nothing you can do about it. I've tested things to where I've had pull downs on the PWM lines to try to keep that from happening. It doesn't stop it. Sometimes when the ESP32 boots, when it goes through its bootstrapping phase, it'll kick signals out on some lines, and it could actually activate the fan. There's nothing we can do about it. It's just the way the system works. Basically, a boot up glitch. And that's just something to be mindful of. That's not a failure. It's just the way these microcontrollers work. PICs do it. They'll have boot up glitches, and sometimes there's no real way to stop it. Honestly, there's almost no real way to stop it without adding additional circuitry like an analog switch, not like an analog switch, but a digital switch for that fan PWM line that you can have it pulled down, and by default, The analog switch is, or the digital switch IC is not to that circuit and all this other stuff. But it's just not worth it for a project like this. It's not really worth dealing with that bootstrap glitch. For one thing, it's not a critical failure. It's not a failure of the board. It's not going to cause a hazardous condition. So it's nothing to really be worried about. Now, if this fan activated, let's say this was like a large blower fan, that might be made out of metal and somebody could lose a finger, then yes, that's something to really look in your design and try to solve and make sure that doesn't happen, because human safety is a vital thing within ISO. You don't want to put something out there that's going to hurt somebody. And it's not just about ISO. Let me be straight. I don't want my products to hurt somebody. But this is a little plastic fan, and you're more likely not to be able to get a finger into the blades. It's such a small fan. And when I get things set up, I'll get my webcam set up, my setup going with my ring light and stuff, so I can better display this stuff. You'll get a better picture. It'll be better images, and you can actually see what the fan looks like in real life. Rather than just images on a screen. Sometimes it's hard to convey some information with just pictures on a screen, without having the physical product of my finger trying to go into the fan blades. So since it's more likely not going to hurt anybody, if anything, it'd be more of a nuisance if it kicked on, and it's not that powerful. It's not even a concern, and it's only 5 volts driving it. So again, you're not even looking at an electrical hazard. OSHA considers 50 volts and above to be high voltage, and that's where you should take in all precautions for high voltage contact. But anything below 50 volts is considered safe. The potential just really isn't there to really hurt you. It's current that gets you, but without the voltage being able to push through the natural resistance of your body, that's one of the things about the higher voltage. Is it has enough potential to actually push through the natural resistances of your skin. And that's where the damage starts happening, is when the potential is high enough to push through that resistance barrier. But when you're talking like 5 volts, 3 volts, even at 5 amps, the potential's not there. The actual push behind it's not there to bypass the natural resistance barrier of your skin. So you're not looking at any real dangerous situations from that. So I'm not even concerned myself with that. So at this point, the fan should not be operating. Also, mind you, this is going to have the UART console involved with it, so we can actually send commands. I was thinking about writing it like an automated test, but no, it'll just be sending it commands to the UART console, which will communicate directly with the driver for this, and you'll get to see how to incorporate the UART console with other header source files into things you want to work on. And it's weird for me saying something like that because I'm not a professional coder. I've been learning this stuff all on my own, teaching myself how to do this, and I was even amazed to figure out how to get it to work. It may not be elegant, but it functions. It works, and that's all I care about. So at this point, it should not be operating. So, load up. So we will want to connect the USB to FTDI converter to, and I forget so easily, connectors and stuff. J4 proper polarity. Load up putty or a similar and connect to the ESP32 serial console with the following settings, baud rate 200, data bits 1, stop bit, no parity. Should reset. Currently, I don't have it. I haven't quite figured out yet how to have the ESP32 serial console actually detect that a serial port connection has been made. And I'm not going to worry about it. Let me buy the N-E-N, or did I actually spell enable? Enable, okay. Should appear on the terminal screen that reads welcome to. Let's not fluff it up. P 101.22.02.501 assembly fan test. Okay. At this, let's change this after this. To this message, type in command get speed. The system return 0. I don't know. I can't remember if I have it like creating like a text string where it amends like 0 and then says RPM after it. We'll go through and we'll fix all that. We'll double check all that when I actually go to write the testing code. Should return 0 that the fan is not rotating, as it should not be. So it shouldn't be rotating because we, by default, it's going to be 0. It's going to be basically turned off. So now, mind you, this is all one word. Let's make sure that's all clear. Because of the way it tokenizes, it uses a space as the delimiter. So you don't want to put an unnecessary space because it'll be an invalid command, because then it'll be basically a command and then 2 arguments rather than a command and 1 argument. So then type in and set speed 20. Set speed 20. You know what? Maybe we should do this to help clarify. I don't know. All right, let's just set speed 20. So basically, what that is doing is so 20 may not be high enough. I'm gonna go 30 again because it falls back to the PWM duty cycle. So what I've set is, so the speed I've got it set up in at least in the file that the firmware I've already written, is that it's 0 to 100, basically 0 to 100%. No decimal. It's just flat out, 1, 2, 1, 2, 3%. And using the map function, a mapping function that is commonly available under C code for C code, I've got it mapped to the PWM duty cycle to properly kind of, because I think I've got 12 bits on that. And so it kind of maps that. So basically I want to set the speed to 30% of the PWM duty cycle. It maps it, and it sets the PWM duty cycle output. So type in the command and argument, set speed 30. The fan should start rotating at this point at a slow speed. Command speed and a value in RPM. So again, I'll have to double check if it's actually amending RPM after the numeric value. So the header and source file automatically goes ahead and converts, takes the pulses, does the math on it, and converts it to actual RPM that it's reading, and it will fluctuate. This value 8. Tolerance of the fan. There are. So there are variables outside of our control, because it's going to depend on the tolerance of the detection in circuitry and other variables such as mechanical variables, because these fans have bearings in them. There might be a little more grease in this model than another model. Temperature will affect it. So I can't really put a hardcore value. And depending on the current airflow conditions in the environment, if there's like a major draft, especially for a small fan like this that doesn't have much power to begin with, it could be affected. So even if you do multiple get speeds, you could get slightly variable results. And that's outside of our control. The main thing is that it is running. Observe the fan for it to verify that it will operate. So you want to make sure that, over the course of a minute that it will continue to operate for that full minute. It doesn't stop. It doesn't sputter. That indicates that the ESP32 is working right. That will indicate that all the circuitry is working right, and that all your connections are fine, and the fan assembly even works. So we'll continue to operate properly. Okay. Type in the command 100, and if the fan is full speed. Now it's going to be hard to tell if the fan speeds up. So basically now we're setting basically 100% speed, 100% of the duty cycle, which should be basically the fan's just full on. Okay, so type in the command get speed. Speed level. Okay. Again, we want to just make sure it operates properly for 1 minute, just give it that time. Now, one last test that we're going to perform on here is 0. and curve if the fan rotating. Should be 0. There we go. So what this is doing is we are just we're basically running the fan through a few quick tests. The fan for to verify that it does not start rotating without any input. So we just want to make sure that everything's operating properly. The ESP32 is operating properly, and the fan's not glitchy or anything like that. So it shouldn't rotate because obviously we set to 0, and the return value from the get speed should be 0. So that is SST14. All right, I saved that, so I'm going to close this. I want to just pull that part number. Again, we'll probably be updating the BOM for the heatsink, but we're not at that stage yet, so I'm not worried about it. I still have to find one, take some measurements and find one that'll fit properly without being too large. So let's go back to here. SST14. Does the fan operate properly? All right, perfect. Now, yeah, it's a long-winded test. Again, if I was using like a LibreOffice Writer, you could fluff these up and make them look really pretty, really organized. Have things spelled a little bit better. Maybe even throw in pictures. And I think for the next video series, when I start it, just drop that information here. And we actually do the other project. I'm going to do it a little bit more flair, a little bit more input, and use like Word and Excel to actually draft up better looking documentation. Again, the whole point of using VS Code for all this is just to show how easy it is to kind of get into it, to actually start covering all your bases with requirements and without spending really any money. I mean, as long as you've got a computer, VS Code is for free. The Markdown language is well documented, well supported. You could Google and search for all the formatting, to get all the nice formatting to make it look pretty at the end of the day. And then I don't think I can open the PDF in here, but then with the other add-ons, the PDF converter, you can convert, the nice looking format here into a PDF for digital storage and or printing. So that's why I'm doing it through here. I know I kind of jumped and changed out of here for like some of the other things, but the main point is I just want to show how easy it is to do proper documentation. There's no reason not to, because saying I have to pay for stuff. If you've got a computer or a laptop or whatever that can run these programs, you've got everything necessary for free at your disposal to write this stuff. So there's no reason not to. Other than not wanting to take the time, and I totally understand, I totally get that, because this is time consuming. But you spend the time now, define everything, and you'll have a better chance in the future with your project. Because once you start selling these, or once you start selling your project on the market, you have other things to worry about with that particular project. That's when all this stuff will help you down the road, all this documentation. You do it now before that project's launched, before it's on the market. You answer as many questions as you can. You test everything that you can, and it's well documented. Also, so if you decide to go for like something like Kickstarter or venture capital or something, if you look toward a big thing, you look for crowdsource funding or whatever, you have all your ducks in there all ready to go. You can answer all of their questions. You're not sitting there panicked trying to figure out how to answer them. You've got all your answers in front of you. So there's no reason not to do this stuff. Yes, it's time consuming, but it's time well spent if what you're doing is important to you. And this project is important to me. So this is time well spent. Yes, I would rather be building and designing. That is what I love to do, but this is also important. This is very important. So that is the fan test. You know what? Let's go disable the top supply and from CN6. CN6. Now in a production environment, we would probably have it set up, and I'm just kind of foreshadowing, and because all this does tie together, and you have to kind of think forward with how you're going to push all this forward, is a test rig, like a test jig, where you can kind of put the board on, hook all this stuff up, flash one set of firmware, which is like your test firmware, which we can do all this stuff. You'll have your since we have pluggables for power, your inputs, your RS-45, and everything else, we can, have a benchtop test where we can test all this stuff with all the pluggables, hook everything up, have workstation set up to do the testing already there. It has an FTDI cable already there, an RS-45 interface. Everything's already set up to go. That way you just plug in, do a couple of things, flash one firmware to it, which is your test firmware, run the console, type in a few commands, basically prod test, and it runs through all this stuff, and you just have to watch it do its thing. And then that's your production test. Then you can flash the last thing is you can configure for out of box stuff, and then flash it with the out of box firmware that basically you want to ship the boards with, and pack it up and go from there. So before thinking, we're gonna have production test firmware that gets flashed, and it's basically as automated as we can make it, and it'll test all this stuff, and there'll be separate procedures for it. But that's down the road. That's not until we're ready. We're getting close to actually wanting to put the product on the market. There's still so many things we need to do. Again, we might not even get this product on the market following proper techniques and processes until around Christmas time. We may not. Maybe a year out. I'm not going to rush it. I mean, when it gets done, it gets done, and we're going to do things right, and it'll get on the market, and it'll be a good product, at least as well tested and vetted as I can. Because one of the things I'm going to do on my own time is once I get a board I can test, I can play around with my own stuff. Maybe we can design some other tests, some like endurance tests, which I think we will. I've got some extruded aluminum and other mechanical parts. I've got screw drives from old 3D printers I've torn apart. I've got belt drive systems. So one of the tests I want to do, and I might as well just, because this sounds kind of cool. So with my 3D printer, one of the things I like working with TPU. And I found this timing belt generator software. Or not software, but parametric on the platform, the Bamboo Maker World. I think it is their online repository for 3D printable models. So some awesome person had created all these parametric models for like timing belts. So one of them you can generate gears, like drive pulleys and stuff, and another one you can actually generate the belts and print them out of TPU. So what I want to do is print a TPU belt and devise a mechanical test for it just to see how durable it is. I might build 2 of them with these stepper motor interfaces, and kind of tweak some firmware out for them, and have one running like a regular store-bought, like Amazon-bought timing belt connected to something that just goes back and forth. And based on, the limit switches that it hits, he can, count how many cycles it's gone through before the belt fails, to see how durable one of these timing belts will be. So that's kind of one of the things I'm thinking about, and maybe even see about adding some, like a mechanical braking system to kind of put a little bit more resistance on that belt to actually force it to work a little harder, so we can test multiple things. So I have big visions, things I like to test, things I like to push out there and try, because this is where I thrive. This is what I love to do. And I really love automation equipment and, working with belts and pulleys and assemblies like that. Because there's other projects I'm working on in my own time, personal projects that are just time consumers. And maybe, who knows, maybe I'll kind of pull them into the mix and make videos of working on them. So that's one of the reasons I'm so driven to build the stepper motor project, is just to have something that makes it easier for me to do testing and playing around with stepper motors, incorporating them in these kind of projects. And if I need to, I will just, design another board for that specific project that takes off of the knowledge I learned doing this, working on this. So that's how I like to work. So that is one of the reasons I'm really driven with this. I'm really curious to see how durable one of those printed timing belts can be. And that's what kind of initiated this project in the first place. Again, I got tired of breadboarding stepper motors, and the wires are crazy. It gets very, very hectic trying to breadboard stepper motor driver, especially one that's feature rich as this guy. Measure all your connections are proper. And if one of your wires comes loose, or you've got a bad breadboard connection, it all just goes haywire. So that's one of the drivers for this project. I wanted something that I could just grab a board, flash some firmware, code it to what I want it to do, and just go without worrying about all the other crap. Just to be honest here. So just kind of the family assembly from CN6. So now we need to, let's go here. We need to test this guy. So we need to devise the test for this guy. So this is going to be a little bit more involved. Because again, I need to learn how this guy works first. So it's going to be kind of crazy. So I have to develop firmware to interface with this temperature guy first. I'm going to have to do that. I'm going to do that on my own time, because that's going to be very time consuming. And what's funny is this board is going to be the only board I have to actually play with this. So I have no breakout board, which I should have probably designed on my own time and built first. But, hey, let's just go for it. So I'll use this first board, kind of cheat a little bit, and develop firmware for this guy. Who knows? Maybe we'll do it on the streams and in the videos. Who knows? We'll see what we do. I'll see how saucy I feel. But I need to, pull the data sheet, see what I'm reading, set up the ADC on the ESP32, get it reading properly, write the source and header file for it, because I want to modulize everything, for one thing. So I want to be able to read this, see how, because I think this guy, let me kind of look now. Hey, you had it before. So I think, so close this. I don't really need that anymore. We've gone through all that. Let me go here to Mouser, pull up the temperature sensor, pull the data sheet. All right. So according to this guy, it should already be calibrated directly to degrees Celsius. So 10 millivolts per degree C. So 20 millivolts on temp 37, and that's not the one we're using. This is temp 36. So we have all this stable with large capacitive loads, should be good. Low self-heating, that's good. Environmental control systems, Okay. So it's already calibrated directly in C, so I shouldn't have to. So they provide a voltage output that is linearly proportional to the current temperature in Celsius, centigrade. So they do not require, okay. So there should be a Right here. TMP 36. Okay. So 750 millivolts output at 25 degrees Celsius. So, yes, I have to Google this stuff. Celsius. So let's say, actually, 750 millivolts at 25 to Fahrenheit. So, like Google. So, 25 degrees Celsius would be 77 degrees Fahrenheit. Yeah, I have a hard time doing math in my head due to various things. I have a hard time keeping track of numbers. So I like to use calculators, converters, and hey, you know what? That's what the internet's for. So at 77 degrees Fahrenheit, this thing should be reading 750 millivolts. So given that, so based off of this, so if we were at 760 millivolts, we would be at 24 degrees Celsius. Or, yeah, 760 would be 26 degrees. 740 millivolts, we'd be at 24 degrees Celsius. So it's good. It's directly mathematically proportional. So every 10 millivolt is a full degree Celsius. So that makes life a little easier. Cool. So we'll be able to kind of do a conversion based off of that, kind of figure out how to map all that. That is not a problem. Not a problem at all. Might even be kind of yeah. This will be easy with knowing this. So yeah, we don't have to do any fancy conversions or anything. Just basically be able to map its millivolt, its voltage range to temperature. Easy peasy. So yeah, I have to just test, verify, basically looking for ambient temperature, compare it to a couple of other devices. But once I verified that, then we can, okay, with the flash the temp test. It was 32. Okay, let's kind of do this. The USB to FTDI roll to J4 rubber T, and then output. Flash attempt test firmware to the ESP. Up. Plenty more. Similar. Settings on the proper COM port. Bad rate. Baud rate 8. It's one stop bit and no parity. Okay. Here we go. All right. So we set the the and curve the Jesus criminy. One. There we go. Okay. So that's what we're going to call it. So before I get too far ahead of myself, let's go back to the firmware directory. Go and create the folders. Fan test. Come on. I think of a test. Temp test. I like how every one of them's like all cap letters except for the hello world. That's just me again. The way I work. All right. So again, those are other tests I have to write and validate and test and get going with, but that is not a problem. So message. Okay. Excuse me. So at this point, geez, pressing NAD. All right. And it was a properly spelled word, so the spell check didn't flag it for me. My goodness. So, okay. At this point, type the command temp and enter. The system should respond, should return that with a thermometer. So let's put this in here because that just kind of flags something else that we need. Now, they do make some desktop or other thermometers they used to. I don't know. That could also measure inside and outside temperature, and they'd have like a thermocouple on a long wire or a thermistor that you would like dangle out your window. I don't know if they still make those, but something like that would actually be kind of usable because you could stick that thermistor to the PCB next to this temperature sensor, and you can kind of read the input, internal, external temperature. But I'll just show you what I'm going to be using. The Amazon. Pain in the butt to have to get going here, but let's see if I can find it. Here we go. Nothing special. So again, this is what I've got, what I'll be using. So it's just a basic desktop thermometer. This was capable of switching to having Celsius readings. Unfortunately, pretty much everything electronic, when you get into engineering like this, everything is in the metric system, centigrade, Celsius, things like that. There are only a few countries in the world, with America being one of them, that still sticks with the imperial system. Sorry, but the metric system is superior. and just better in the long run. It's just easier to understand. It's all base 10. And it just makes more sense. But that's why you see a lot of the engineering, all your electronic parts, everything's measured in the metric system. Everything's measured. All temperature ranges are typically measured in centigrade, Celsius. All your dimensionals are millimeters, or all metric. So that's one thing you have to get used to, is using the metric system and understanding it. Now, it is hard to do the mental gymnastics to convert centigrade, Celsius to Fahrenheit, the numbers we're used to. But roughly 22 degrees Celsius is room temperature. The temperature that's typically comfortable for most of us. So just keep that in mind. So I'm going to be using that a desktop thermometer, basically reading C ambient. So technically, because the way this is built, we're not really driving the stepper motor, and the heat in this board should be minimal. So they should be closely aligned. Let's just see, is closely aligned with the dust within a few degrees. So you will have some variation, because the board, because of the thermal mass, all this copper, heat will move around. It will eventually all warm up. So this could be slightly warmer than room temperature, but you're only talking maybe a couple degrees at most, because the only things really operating or doing anything right now and really pulling any kind of power, the 3-volt power supply is really, it's delivering power, and mainly just to the ESP32 and the temperature sensor. The stepper driver isn't doing anything, it's sitting idle. This isn't really doing anything, it's sitting idle. It's just pulling very minimal, like sleep current. Just sit there, hang out, do nothing. And you were talking very minimal current, so very minimal power draw. The only things, like I said, really doing anything are the ESP32 and this temp sensor. So you should only be within a degree or so of C. We could even use a multimeter with a thermocouple on it, and kind of get a third party. My multimeter also has an internal temperature sensor, so it can read the ambient temperature along with the desktop temperature sensor, along with the external thermocouple. So we have all these comparisons if we choose to. Maybe we'll expand on this. But for now, we'll just kind of leave it here, because I still have to write all these tests and do all this validation. We can even set up the firmware to convert it over to Fahrenheit, do the math for you. You could do that. I can even show you, a command like set unit F or something. And then the firmware can automatically know, hey, this flag is set, so any data I return is, any string data I return is going to be set to Fahrenheit. But, that's fancy stuff for later. We're not worried about that. So at this point, let's get this SST15. You know what? No, we need to expand on this test. So we need to kind of warm up the temperature sensor just to make sure that it picks it up. Now, there are a couple of ways we can do this. We can use a hot air gun on low and just kind of just warm up the temperature sensor and then take a reading. So let's go ahead and do that. We just want to make sure it is actually detecting temperature changes. Let's see here. Hot air gun with control. So we want to make sure we can drop the temperature down. Believe it or not, they actually make some really, really calibrated and controlled hot air guns that you could set an actual temperature to, and they will maintain that temperature. They're really nice, but they're pricey. I've got a simple one off Amazon that just has a little dial for hot and cold, and just kind of set the temperature gun to a low setting that does not burn you, and apply the hot air to the... So I'm just putting this as a placeholder. Set it to a low setting. We'll kind of figure out a temperature we can set it to and use a thermocouple to kind of measure it. And we'll get into fixing this and rewriting. I'm going to do some tests with my my multimeter, thermocouple, and my hot air gun, and kind of see what kind of temperature. I'm just putting this in here. I'm just kind of putting this in there as and apply the hot air to the PCB sensor. Let's get the part designator out of here. IC7, and hold for 30 seconds. That should be long enough to warm up the temperature sensor. And then type the command. Actually, we're going to make that all lowercase. I can update the firmware so it doesn't care if you're uppercase or lowercase, because they are different ASCII characters. I should be able to set it up so it doesn't care. It can convert the case automatically. And the ESP32 should, with a higher than the... Okay. Allow the PCB cool for 5 minutes, and then type the command temp should respond with a value closer to the initial, to the first so it should be closer to ambient. So by your closer, desktop thermometer. There we go. So it should, after you've let it cool for 5 minutes, it should be back down to ambient, and you should be able to get the temperature, and it should be closer to the desktop thermometer. 5 minutes should definitely be long enough. So, some of this stuff is waiting. So let's make sure that is in the sheet. 15. Okay, does the temperature sensor operate properly? So let's go through. I'm going to drag this off my screen so I can, use it to reference. That way I'm not flipping back and forth like a madman here. I'm already crazy enough. I don't need to drive you guys crazy. So let's go through the schematic. Let's go back to the ESP32. So mind you, these are subsystem tests. So we're basically just testing the subsystems associated with the ESP32 because we've already tested the power supplies and stuff. Again, these are non-destructive tests. So the first system test is actually the USB UART. Does it recognize newly connected serial port, which is important? And then we throw on the Hello World firmware, basically to the ESP32, and then we connect here. And, well, we don't even connect here yet. So the Hello World just tests that we can flash the ESP32, the fresh ESP32, and we get a kickback basically through VS Code. That, you know, through the terminal here, that it does work. Okay, so we've tested that subsystem. URF TDI, we're going to test this subsystem here. I should put a space in there. That's not all one word. Okay. Then the next thing is status test for this LED. Then the next portion is subsystem is the RS45. The limit switches CN3, 1, 2, and 3. These inputs. CN4. Well, okay. Then we're going to do these inputs, but with a PLC as a control source to make sure that you can actually have them backwards, that the optos are operating properly. Because again, they're AC input, so you can, even though they're defined as anode cathode here, it's actually negligible. It doesn't care, because they're AC, so you basically have two LEDs in there in opposite directions to handle AC. So we have that. Does a stepper motor. Driver chip operate properly? In other words, will it drive a stepper motor? Then we're testing the fan assembly subsystem. Perfect. And then we're testing the temperature subsystem. Temperature sensor. So based on the schematics and everything else, that is all the core subsystems that are on the board and that we want to test and validate. So that's all our subsystems tests. So delete rows. All right. So we might kind of rename some of this stuff. Like initial, or maybe we're going to actually draft up a new test plan. We're going to call it the deep, we might even call it the destructive test plan. Performance requirements, okay, blah, 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 blah. Because we're going to be testing some of the more hardcore systems in here. Additional tests we want to draft up. Because one of the things we'll want to check is reverse, we'll want to try pushing the voltage up, for one thing. Hit 30 volts, which is the maximum voltage my power supply can push out. We'll want to reverse the voltage inputs on here and make sure the reverse voltage protection actually works. We'll want to see another thing that they make, which is kind of cool, is they actually make what's called an ESD gun. An electrostatic discharge gun. It's really cool. It's for testing this your TVS systems. So basically, as a little device, if I remember right, we actually had one at one of the last companies I worked for, and it would actually put out an electrical discharge to simulate like you walking on carpet and touching the board. And you could use it to test like inputs, like anything that you say are TVS protected. You could actually test to verify your TVS diodes are working properly. I wish we could test that. I mean, we could if I got a small carpet and, kind of charged myself up and did it, but I don't like shocking myself. I'd rather have one of those ESD guns. I'll kind of do some digging to see if I can find one for relatively cheap. Because, again, we still got kind of, I'm still looking at possibly releasing within a year. So we have plenty of time for testing. But so we'll do some potentially destructive testing. So that's going to be a different test plan, different log for it. We'll test like shorting things out, seeing how things handle stuff here. We'll already be able to test reverse voltage, so that won't be a problem. We can even test an AC input, which would actually be kind of a cool idea. On those guys, USB UART. Again, I wish we could do testing with an ESD gun, but there's not too many destructive tests we can do with that. Stepper driver, we can definitely do some potentially destructive tests. Again, one of them is running this thing as hard as possible. So I'll have to probably devise a mechanical application to basically mechanically break the stepper motor to give it really heavy physical resistance. There's multiple ways we might be able to accomplish this, and I'll look into it. But yeah, we will find ways to basically push the stepper motor, the stepper driver to its limit, just to see how it does. We'll have firmware that'll monitor it, additional firmware that, again, it's going to be individual firmware. Maybe we'll raise the temperature on the hot air gun, maybe to the point of almost pulling this IC off with hot air, just to see what happens, just to watch. So those are kind of things that we want to test, and they should be a separate test plan, a separate test log. We can call it like, I don't know what kind of name, but, destructive testing, system intensive testing, that could, we'll come up with a name for it. But before we finish this out, let's kind of say that we've got here, let's look in the performance in the requirements documents. Again, we might kind of clean this up here. Functional performance, yep. So safety, so this can actually be part, some of these safety things can be part of like the reverse thermal protection, isolation. So like I said, we'll push up voltages, we'll see what happens. We can even kind of like inject some voltage to the output side of this and just see what happens. To make sure there is proper isolation between this and the logic side. If like somehow somebody applies like 30 volts or 24 volts to these motor leads, things happen, or equipment failure causes that to happen. Does it, it may destroy the stepper driver, but does it destroy the rest of the system? Does it cause a cascading failure where it can damage other things connected to it? That's what we have to consider. Now, even though realistically, yeah, it would probably destroy the stepper driver. And if you wanted to rework it, you could with hot air, but because of the way this thing's going to be heat sinked through the PCB, mind you, that's a lot of thermal mass that this thing is tied directly to. Hot air rework is going to be difficult. Every other part on here, yeah, you can hot air rework, soldering iron rework. But this guy would be extremely difficult to rework because of, it's just going to be, you're fighting entropy trying to rework this guy. All that heat you're applying to pull it off is going to be pulled directly into the ground plane and it would be distributed along this whole board. So sometimes rework is not possible because of things like this. Even the ESP32 would be difficult because right here, these ground pads are going to be tied directly to the ground plane through that big copper pore and these heavy-duty vias. So even reworking this ESP32 would be difficult. That's unfortunately the side effect of modern electronics. With through-hole parts like back in the day or more simple SMD devices, reworking and repairing boards was a lot simpler. But with the newer designs, these heavier pads, all this thermal mass to help do everything, it just makes it harder and harder to actually fix boards. And unfortunately that's what causes the waste. That's why I really believe in recycling and properly keeping the stuff out of landfills. Now, if you got like this part failed and if you felt saucy, you could use hot air and was careful. You can like pull these optos off and use them for other development because more than likely they're not going to be damaged. Some of the other components you might be able to pull off with hot air and reuse them in like a breakout board for testing other things, experimenting with things you don't care about, that you don't have to use new parts for. So it's not like you couldn't salvage parts to use in other experiments and stuff, but it's just a lot harder nowadays. So we're kind of done with the schematics for now. This will be kind of on the deeper test. We'll have a whole new test plan. We're going to rename it something different. We're going to have a whole other log file for it. But before I get there, while we're still kind of here, I'm going to go and close KiCad. We don't really need it right now. So let's kind of say this is done. Let's go and clean this up a little bit. Delete rows. kind of, you know, make it a little pretty. Again, if we have to come back and revise this, that's fine. So let's kind of make this more usable. Because remember, again, there's no real tie into anything here. And that's why I leave all this blank space up here. So, project ID number. So let's kind of doctor this stuff up here. Merge cells. Throw that over there. Merge cells. We'll kind of put that there. Format cells. Let's give them a border. Okay. So it's project ID number. You got it up here, but sometimes you want it here. So this is going to be E101 22.501 cells. Project revision. 1. Hey. My enter key likes to stick sometimes. Let's. That's why I like doing this, and then coming here and doing that. Format cells. It's project revision, but we also have PCB revision. Because the project may not have changed, you know, the overall project may not have changed. No, let's actually just name that PCB revision. Let's just name it revision. Revision 1. All right. So what we're going to do then is merge those cells, merge these cells. So we don't have to kind of push too many things around. All right. So we're going to be, this is basically 1 log per board. PCB serial number. So it's whatever board serial number, which we'll get to when we actually do that. There's some stuff over there. Merge cells. Yeah, I know it's kind of crazy, but we're going to format. We're going to throw borders in. Basically, kind of make this look nicer. Drag these guys down. Slam that over there. Let's go do that there. Do that over here. Tested by. Tested by. Tested. Test date. So hopefully all this gets tested on the same date. So let's see here. Overall test result. You can pass that. See again. So we have all this blank space here. I don't know if I really care about all that blank space there. Can I? Well, I mean, we could kind of merge and center, merge all this, merge cells, center line in the middle. test plan log. Let's just be official. Let's just go that way. Bold it. We're going to. All right. Now let's just kind of pull out like an indigo. Let's just go here. No, I don't like the fill in. I'd rather test it. Fill in with that blue, like a blue. There we go. All right. So we're gonna put the border around it. Okay. Down here, we're gonna. Do I have a footer format? So we can go to headers and footers. Right area. Version 1. So that'll be in the footer if you go to print this, convert it to PDF or whatever. So the whole idea is to have one test plan. Okay, right down here. Let's go back. Nothing looks like I changed it there. So here, test plan log. Then up here, required materials. Test plan log to store. Use one test plan log file per PCV serial number tested. Yeah. So basically clarify that if you're testing two boards, you have two separate test plan logs. So basically what we can do then is required materials. Let's do this. 1, 2, 3. So prior to test. We'll change that. So prior to testing, open a fresh copy of fish. Boy, I just invented a new word there. Copy of, and then save it as log where X is the serial number of the board that the test log is with in the. So we're going to do firmware, server controller, project documents, test logs. I'm spelling that right. All one word. And documents. Just test dash logs. Logs folder. All right. So basically just spelling out that, you save it as the serial number, basically for traceability and accountability. and it ties that test in with that board. Yes, you're duplicating information here. Yes, that's the way it works. But that way, if this is printed out, because you're not, when it's printed out, dumped to a PDF file or something, you don't get the information that's with the file up here. Revision 1, okay. PCB serial number, okay. So that should have all the relevant information for this. Let's just go ahead and home P101 0.501 test plan log. Boom. All right. So now that's a little prettier. It's more functional. Things are cleaned up. Let's kind of, get things a little bit spaced more appropriately. Boom, 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 boom. All right. So again, this might change as we move forward. Discover tests we should have done once we build the board, but we should have everything, covered. Visuals. Here's all the resistance tests. Performance requirements. So this one may not be applicable to this one. These may not be applicable to this test. These are going to be deeper tests. So you know what? Let's get rid of them because they don't apply. We didn't write any tests. And again, some of these are going to be what could be destructive tests and require other firmware, and they're more advanced testing. This is all like initial testing. Basically, we're just kind of prove that the design actually works. So let's get rid of that. Let's simplify our life. Those we can throw in other test plans, other test plan logs. Because some of that's just firmware. That's testing firmware. That's totally different testing structure and setup for what we're trying to accomplish with this test plan. Again, we might rename everything, kind of clean things up, but we'll go from there. Right now, the great thing is it's all malleable. It's all in a state of flux, so it's not going to be a big deal. So we'll stick with that. That looks good to push. I'll push all this out. We've got that. So for the next video, maybe we'll start writing the other test plans, the more destructive tests, because I'm really hoping that I can get the boards in on Monday, and maybe we can build our first board. Maybe we can do it on Monday, depending on what time the boards come in. We'll see what happens. We'll see how it goes, but we'll definitely have to check in the boards and do our incoming inspection on those, follow the process. But for now, I thank you for catching us out and hanging out and checking out these videos. So we'll see you tomorrow afternoon in our Twitch stream, and have a good rest of your afternoon.